Hello. This video demonstrates the use of a spreadsheet for looking at lighting power density. Lighting power density is the ratio of lighting power to the square footage area. So we measure it in how many watts per square foot. A 100-watt light bulb in a 10 by 10 room is 1 watt per square foot. And in this scheme, which is similar to figure 14.3 in MEB, in this scheme, we look at lighting as being supplementary to daylight, so we need less closer to the daylight source at the perimeter of the building where the windows are. So defining the building in 3 zones as perimeter, interior, and core, we can assign preliminary estimations of lighting power just to see what the repercussions of these kind of decisions and targets are. There are ways of identifying what these should probably be. We'll talk about those. And for a building of a given size and a given floor-to-floor height, we can define how deep each of those zones are. So if the perimeter extends 12 feet back from the window, in the interior zone where there's some daylight, another 15 feet beyond that, the rest being core, 40% being glass. This isn't for daylighting purposes in the spreadsheet, it's for balance point and heat gain. Now we generate 25 different schemes by saying we're going to start with an aspect ratio of 1:1 and increment it in this case by 0.5 per step. So it'll be 1:1, 1.5:1, 2:1, etc. We're going to start with a 3-story building and do 4 more scenarios based on incrementing that by 1 story per step. So 3-story, 4-story, 5-story. Assign our R values. Look at the occupant density, how many square feet support each occupant. Design temperatures for inside and out, and the internal heat gain from plug loads and equipment. This is a pretty good starting assumption. In office buildings, this is a number where everybody has a computer. Of course, this might be a really large number, but for starters. What the spreadsheet then gives you back after those inputs is the overall dimensions, length and width of the building for all 25 schemes, depending on the aspect ratio and the story height you're interested in comparing. The amount of wall surface area in each of those, the surface to volume ratio, which is the square foot of skin it takes to enclose a cubic foot of internal space, and how much of the building floor area is in the perimeter daylit zone, how much of it is in the corresponding interior zone behind that. Then thermally, on this third sheet, you can see the resultant amount of lighting power, lighting equipment, lighting energy you need in the building, and the resulting air conditioning load in tons that come directly from waste heat from those lights, assuming they're all on. The corresponding watts per square foot of lighting power density in the building. So you divide this by the number of square feet to get that. Surface cooling load, heat gain through the skin from temperature-driven differences. The balance point temperature and the internal loads, which you see are the same for all the schemes. So we have other tabs here that teaches a little about the concepts and terms involved, and even some tips on how to exploit the spreadsheet a little bit. And the input screen. That's all for lighting power density.